In this third video, we'll present semantics for mini-while with shared memory. So we'll start from the mini-while language we have used in the previous courses. So we first recall the syntax of this small language. There are expressions that are arithmetic expressions with variables and constants. And then we have the statements. We had the assignment of expression to a variable. We had defined simple function call in a previous course. We have a skip statement that does nothing, and we have a sequence. We also have a statement for tests and a while statement. In the shared memory setting, we will not consider function calls, but we will use them later on. Again, when you have function calls, your programs look like that. If you don't have function calls, then you just have a set of statements as a program, or just a body if you prefer. So the program has a set of variable declarations, a set of function definition, and the body of any function or the main body is a set of variable declaration and a statement. The variable declarations looks like this, and the function definition is just a set of function definitions of this shape, which is to is a return type, f is the name of the function. We have a set of parameter x1 to xn with types, and then inside the function we have the body, and there's no return statement. So in fact, we enforce the fact that the return statement is at the end by defining function definition this way. This whole has been defined a bit more carefully in the courses on functions. If you don't recall all that, you might want to have a look at the video for function definition. So let's now recall the old operational semantics, but without the function, because that's what we want to modify here. So we'll focus on small steps. That's what is interesting for us here, because we said in the previous video that it's not easy to define a big step semantics for parallelism. So we call that in semantics we have a configuration that is a statement and a store. The store maps variable to values, and the statement is what needs to be evaluated. And the configuration is either a couple statement plus store, or just simply a store, which is generally for the final result, for the final computation of one statement or the current body. So the assignment is simple. It just starts from one store and says the new store is an old store where x is modified. And we call that var a sigma is the evaluation of an expression a in the store sigma. All that has been defined more in detail in previous courses, but skip does nothing. It just returns the store as it is. We call the sequence that has two cases. If you have a sequence of S1 or S2, either S1 can be reduced in a single step, in which case we still need to reduce S2, or S1 cannot be reduced in a single step, in which case we just reduce S1 of one step, and we will continue with whatever remains of S1. The conditions look like this. If we have a statement of the form if B, then S1 else S2, then we first evaluate B in the store sigma. If it returns true, then we'll evaluate S1, and if it returns false, we will evaluate S2. I omitted here the statements for while. You can find them in the course that defines the small step semantics for mini while, and there's no special case that needs interest here about the while statement. Extending mini while with shared memory is quite simple, so it all fits in this slide. We first extend the syntax with one new construct that consists in putting two tasks in parallel. So we have this new construct, parallel, that puts the statement S in parallel with another statement S prime. So the statement now is whatever you had before plus the parallel composition of two statements. Concerning the semantics, we need basically two rules for parallelism. The first one, consider the case where if you have a composition of two tasks, the task on the left can do one step. This gives you as one prime, and you just do this step and you keep the produce store. The second rule does exactly the same, but in the case where it is the task on the right that progresses, leading to a new. The reduction of a task either lead to a statement store or just to a store when the statement is finished evaluating. This corresponds to the end of one of the two tasks in the parallel statement. So if you have this task that corresponds to statement S1 that finishes, then you just discard it and you just continue evaluating only S2 in the new store sigma prime. And same thing if it's S2 that finishes. Just a small addition. Sometimes the parallel operator is not often practical in the syntax because of the question on whether it is associative, commutative, and how it composes with the sequence, for example. In languages, you would mostly have a spawn statement that just spawns a new thread, and you can simply add it in the syntax and obtain a syntax that looks much more like what you have in classical languages. And you still keep S1 parallels 2 in the syntax for at runtime, but the program just writes spawn, and you have this rule that just transforms the spawn into a parallel statement. So what I suggest in the following is to use the semantics we've seen to compute the behavior of this program. So here is the spawn version if you want to try it. As usual, I suggest that you do it and then I give one correction on a tablet. You will not be able to compute all the semantics, but you should be able to compute a few of them, or at least see where options are possible.
So we are trying to compute the semantic for this term and we place ourselves in an empty store. So first thing we have to do anyways is to do the assignment to 0. Most of the time I won't detail the premises of the semantics, but I will just do it here. Here we want to do a sequence between two things, and this leads us to evaluate x becomes 0 in the empty store, which leads us to the store x to 0. This is done by the assign rule, so it's assigned here. Then we obtain the resulting term, which is the other part. So we reduce this. So which is the other part, x become 2, then x become x plus 1 in parallel with x become 3. Generally, we suppose that sequence has a higher priority, so this means this. And we are in a set in a store where x is bound to 0. This was the application of sequence rule. Now I will just unroll the different states because what leads to the reduction is not always very interesting and takes time for not much. So now what I will do is that I will do here the x becomes 2 parts, so I will decide that I will reduce this one. So if you have a look at the semantics, it gives it is in fact an application of the parallel one rule. So in fact this is done by using parallel one and of course sec and assign. So this leads us to the new state, which is x become x plus 1 parallel with x become 3, and this is in the store where x is bound to 2. Then let's decide that we'll do the parallel 2 now, so we will try to reduce this part, so we do parallel to and assign. So you agree these are the sequence that are done vertically and that I just keep here. So then we would reach the state where x becomes x plus 1 is the statement, and I'm in a store where x is 3. And that's it. So we just have the last state, which is simply an assign. And we reach the state where now x is mapped to the value 4. So that's it. That's one possible reduction. Of course, you can notice that 3 was a possible result too, because to obtain that you would just need to exchange those two steps of parallelism, and you would assign x to 3 and then x to 3 again. So that's it. That's for this first term. I will do the second one, but before doing the second one, you might want to check the version of the slides. I added an x equals 0 at the beginning so that the semantics is a bit clearer and the example is more interesting. So this is a video about the second example of the mini-while concurrent semantics. I will not detail the premises in this video and just say which rules are applied as a bit as I used to do, but not even detailing the first case. I guess you get the semantics principles by now. And especially the first part because we start by a sequence with an assign to x of x to 0, so there's really nothing fancy here. So that's I even denoted S for the big while statement to simplify all the next development. So for example, now I could start to try to evaluate the while, and in one step you would check the conditions and unroll if necessary, which is the case here. So this is in fact parallel to and while. We obtain. Now we could still do parallel to, which leads us to a sequence of with an assign. And this leads us to the configuration. Now we can unroll the while again. And let's decide we now go to the first branch of the parallel, which is directly an assign. This finishes the left branch, so we are left with x become x plus 1 followed by the while, and x is mapped to 2. No, I don't have parallelism anymore, so we are back to classical sequential calculus, and so we will get to the S where x is mapped to 3, and this will finish the while. So x mapped to 3 is a possible value for the store at the end. In fact, if you look carefully, x mapped to 2 is also possible. Indeed, if you delay this one and you still do parallel 2 all the time, as much as you can, then you would reach 3 anyway, and then you could do parallel 1. That is the case for obtaining 2 globally. Okay, so we played a bit with this parallelism and with this concurrent while language with shared memory. So that was the second example for the semantics.
So now we define the semantics for while with shared memory, and we've seen how it can be used on an example. We will, in the next video, focus on the semantics for futures in the case of mini while.